We're now going to continue with our discussion about cryptography, and first starting with a consideration of the mathematical basis for cryptography, which was first proposed by Claude Shannon in 1945. So we've covered two different types or approaches to ciphers called substitution ciphers and transposition ciphers. And essentially, Shannon outlined the basis for why these work and what the aims of these two approaches are. And he termed these properties confusion and diffusion. So confusion is essentially the substitution process that we go through. And what this results in is a property that the ciphertext itself depends on several parts of the key. So to be effective, then each bit of ciphertext should really depend on parts of the key. It also hides the relationship between the ciphertext and the key, making it difficult to take the ciphertext and then reconstruct the key. Diffusion is another property which helps change the distribution of plain text in terms of where it actually has an effect in the ciphertext. So what you want effectively is to have the plain text impact large parts of the ciphertext and not just the chunk it's immediately concerned with. So modern cryptography and ciphers use confusion and diffusion to great effect. Before we look at those, however, let's just consider what we're actually doing on a computer when we're dealing with text. So text in computers, as I mentioned before, is represented by ASCII or Unicode code. And so this is a digital representation of each of the characters, the printable characters, so the alphabet and the numbers, and also other characters like non-printable characters. So every character in the character set has a digital representation, a number. So A, for example, is 97 in decimal and 61 in hexadecimal, and in binary it's 11000001. Now I'm not going to go into the number representation systems that we're using here in terms of decimal, hexadecimal and binary. And I suggest, though, if you're not familiar with it already, that you do actually look at some resources on the internet. When we encrypt text on a computer, we take the keys binary and then do a logical operation, either an AND or XOR, using the key on the plain text. And just to remind you, if you're not familiar with what these logical operations do, an AND takes the two values, and if they are both true, then the result will be true. So in the example here, if we have plain text which has a digit 1 and the key has a digit 1, the result will be 1. In all other cases, the result will be 0. So both have to be true or for the result to be true. In an OR, it is, as the English sort of suggests, either of the inputs can be a 1 for the result to be 1. And in fact, both of them can be 1. And in this case, we have three results that are 1 and 1, 0. And finally, in the XOR case, this is that you have to have only one of the inputs being true, or 1 for the output to be 1. So we can see here that if both inputs are 1, the result will be 0. If the plain text is 1 and the key is 0, it'll be 1. Plain text 0, key is 1, it'll be 1, etc. So to encrypt the letter A with the letter T, we can do the AND or XOR. And if we do an AND, we'll get the output as a backtick mark, which is hex 60. If we do an OR, we'll get the U, the letter U. And if we do the XOR, we'll get a different result, which is actually hex 15, which is a non-printable character. So we tend to use XOR and not AND or OR. And there's a reason for this. So basically, if we take an image which is represented in fact by a set of bits or binary data, and in this case an original image of Alan Turing on the left there, and we take a random key and encrypt it using an AND operation, you can see the second image that large parts of the image are still visible. So in effect, it hasn't changed all of the bits to something different. It's basically retained some of the bits with the values that they had before. Or is even worse, and you get an even clearer image of the original image there. When you use an XOR, however, the image sort of disappears, and we've had a much more effective encryption than with the case of and or. Now, there's a reason for this. If we look at the logic tables of AND, or the truth tables of AND, or, and XOR, what we can see is that if we look at the inputs of the plain text and then compare it to the outputs in the ciphertext with this particular key that we have here, with the and or operations, we get a probability of 0.75 or 75% chance that the output will be exactly the same as the input. With an XOR, however, that drops to a 50% chance that the output will be the equivalent of the input. So essentially, and or, when you encrypt using those processes, leaves a lot of the original plain text unchanged given a particular key. Now, with modern ciphers, you can do we're not doing just a simple operation like this. However, it's always not a good idea to start off with the weakest form of operation, and XOR is the favored approach. There is also a computing technology perspective of why we use XOR, because it can be implemented very easily in electronics, and we'll look at that when we look at PC hardware. So modern ciphers come in two different forms. There are symmetric key cryptography approaches and asymmetric key cryptography. So in the symmetric approach, and we've already dealt with this approach in terms of the Visionaire cipher, for example, or the Caesar cipher, the key is shared by both parties. So we have a single key, and both parties know it. So one party encrypts the communication with that key, and the other party uses the same key to decrypt. In asymmetric key cryptography, each party has actually two keys, and they're known as a public key and a private key. We'll go into the details of how those are used, but it's just important at this point to remember the distinction between the two. Both the types of encryption are used for different purposes and different benefits and drawbacks. They were brought about, or essentially invented and used to solve different problems. In addition to the above, however, there are other cryptographic functions that don't require a key, and also very important, but one of them is called a hash function, and we'll look at that as well. So looking at symmetric key cryptography, obviously the need arose to have these type of ciphers when we had digital systems, and they come in two different types themselves. One is called a block cipher, and the other is a stream cipher, and they differ in how they approach handling the plain text. So block ciphers take chunks of the plain text and manipulate them to encrypt them. Stream ciphers encrypt data as a stream of bytes. So you can think of the difference of block ciphers are essentially, you've got the file there on your disk, you can chunk it up into blocks, and then you can encrypt it. With a stream cipher, you've got data which is arriving as a stream. So think of streaming audio, for example. Data is arriving to your laptop or your phone as a stream. Streaming video, it arrives as a stream. That's where the concept of streaming data came from. And we have to handle that differently because we don't have all of the data when we start encrypting. The data encryption standard, DES, became the first US national standard algorithm in 1976, and so this is how long this has been about. It was invented by IBM, and it was originally called Lucifer, and that was based on a cipher invented by a man called Feistel, and so it was known as the Feistel cipher. It became a little bit mired in controversy because during the development of the cipher, the US National Security Agency, the NSA, insisted on being involved in the design and decision about certain elements of it, and especially about the key length. And so that raised suspicions that they had chosen specific key lengths and designs that would enable them to essentially break the encryption and so weaken it. So fine if you're part of the American government, not so good if you're anybody else. So DES operates on a block length of 64 bits, and it uses a key length of 56 bits. And we'll see that key length is critical to how strong a cipher is. And 56 bits, as we'll see, is not very long. So in fact, the key is 64 bits, but 8 bits of that are used is what's called parity. That's for use to check that errors haven't occurred when the key is used. So effectively, it's 56 bits long. The process that it uses, and we don't really need to go into too much detail about this, but we'll cover the principles of it, is that it takes a key, and the first thing it does is generate subkeys from it. And it does that 16 times to actually then operate on the plain text. So that's important. And this is part of going back to Shannon's idea of confusion, that we have lots of different parts of the key get involved in encryption of lots of different parts of the ciphertext. So permutations, diffusion, is done by initial expansion through duplication and mixing of outputs at the end of each round. So it goes through a whole bunch of rounds of encryption and does various things with the keys and with also with the actual plaintext and output from these processes. And it uses a substitution round as well, using what are called S boxes, and which are lookup tables, and they take in 6 input bits and output 4 output bits, and they're a bit like essentially a mixer. They essentially take input, mix it up, and take some output, and they just applied multiple times to try and increase the effectiveness of encryption and the inability to actually reverse the process. When you take a single block of plaintext, that's the process, but what about a sequence of blocks? So in this case, we sometimes use what is called an initialization vector, or referred to as a seed. So you'll see in encryption ciphers the use of IVs or seeds, as they're called. And they're used to inject, again, a bit of randomness in the process, so that if you're using the same key to encrypt lots of different files, for example, you can use different initialization vectors, so that if somebody compromises it makes it harder to get lots of different examples of encryption and then work backwards. So DES and its variants that followed have different modes of encrypting. And even though there are a few of these, the important things to remember out of them is that they take slightly different approaches to essentially taking a sequence of blocks and encrypting them. Some have a chaining effect, so they take the output from one block and then feed it into the next. Others operate on blocks singly, and we'll see why that may be a problem. And they can be used in different situations, and so they're optimized for different uses of the encryption. So the key thing to remember in all of this is that these modes are effective in different situations, and so the important thing to understand is why you would use these in particular situations and not necessarily the absolute details of each approach. But let's look at a few of them in any way. So in ECB mode, the first one, electronic codebook, each block is encrypted independently. So we take the plain text, we apply the key, and we get the ciphertext for each block, and we combine them all at the end, and that's a ciphertext. And that's great because they're all done independently, and as we'll see, that sort of saves you from getting errors that propagate. However, it does have some problems. Cipher block chaining, on the other hand, uses an initialization vector to start the process off. It XORs that on the plain text and then applies the key to that block to produce the ciphertext. That is then used as the input into the next block, and the process is repeated. So that's great in the sense that, again, we don't have independent blocks, and so essentially you have to start from the beginning to unencrypt. You can't just take a random bit of ciphertext and hope to unencrypt it with your key. Cipher feedback does the same thing as CBC, but operates on a stream of real-time data. So again, this is optimized for stream data and not block data. And it has a slight different arrangement in terms of how it uses the IV and keys. Output feedback, same, but uses, again, a slightly different approach. And then there is a counter mode, which is the same as output feedback, uses a simple counter to alter the seed input to each encryption. So again, the reason for this is that we can use some of these modes and parallelize them so that they can become very much faster. So I said that there were problems with using the electronic codebook mode because even though it's simple and it essentially encrypts each block separately, you can see here that the problem with it. So we take again an image, in this case the Linux Tux penguin, and we encrypt it using a DES and ECB mode, and unfortunately we still see the penguin in the result, which means that it has repeated some of the key. When you use the same parts of the key on the similar sort of areas of plain text, you get the same ciphertext coming out, and that results in an image being visible. So CBC and CFB mode propagates errors, and this will corrupt attempts to decrypt. So if you get some errors in chained modes, they will propagate, and so that's a problem. OFB, output feedback mode, doesn't propagate errors in blocks. And then finally, ECB and counter modes can be parallelized and so are fast. So we'll see with the difference between symmetric and asymmetric encryption that there is a major difference in speed. And when you're doing encryption, speed becomes a major factor in your decisions. Unfortunately, and possibly not to do with the fact that the NSA interfered, DES is broken. The DES key length became a liability, and DES was cracked in 1997. So essentially, because it uses a 56-bit key, there are at most 2 to the 56 different keys that can be generated, and so all you need to do is go through all 2 to the 56 attempts. Now, having said that, even with a reasonably powerful GPU, a graphics card, NVIDIA 3090, although I know that all of you have gaming computers that have one of these cards in it, if you decided to crack a bit of encrypted text using DES, it would take you 166 days to do that. However, add more GPUs, you can do it faster. So they did that, and DESCall reduced that to 96 days. A year later, they reduced it to 56 hours using FPGA hardware, which is a different approach of hardware and used in things like cryptocurrency mining, for example. You can get it down to 6.5 days. But if you know the plain text and you encrypt that using the cipher that you're trying to crack, you can do what is called generating a rainbow table. So you pre-generate all 2 to the 56 different versions of ciphertext from that examples of plain text. And then if you get some new plain text, you can just look it up in the rainbow table, and that takes about 25 seconds. So just using a large GPU machine on Amazon Cloud, AWS, and a program called Hashcat, you could do DES in about a day. So it is not secure by any means. So the solution to that was to do DES 3 times in a row, and that became known as triple DES. You don't do double DES because there's a vulnerability with that approach called a meet-in-the-middle attack, and essentially that just makes it no better than DES at all. It doesn't improve the situation. So the point to remember there is that why double DES is not effective. Excuse the typo, variants of triple DES depending on the number of keys and whether you use 3 encryptions, or there is a variant of triple DES that where you do an encryption, then you do a decryption, and then you do another encryption. It's sort of counterintuitive, but that works in a different way, but as effectively as 3 encryptions in a row. However, DES had been tarnished, and even triple DES was a problem, and so a new standard was adopted. They went out to the NIST, the National Institute of Standards Technology, went out and in 2000 and for a competition to get a new encryption standard, and adopted the AES standard, which is based on an encryption scheme called the Rindell scheme. So this uses a 128-bit block length, and then it has optionally keys of 128 bits with 10 rounds of encryption, 192 bits with 12 rounds, and 256 bits with 14 rounds of encryption. So we're already massively improved on the 56 bits. And remember, each bit that you add, because it's raised to the power of 2 to the power of the key length, you get a much larger effect. And 256 is considered uncrackable by most, brute force certainly.